Hi, welcome to Inside Out Math. This is a second set of videos on double integrals over general regions. Instead of integrating over a rectangular domain, which we've been doing in iterated integrals, we're going to integrate over any shape we want in our domain. And a couple of recommendations before we begin is you get your integration technique straight. This is a section on integration, so it's important that we keep practicing our integration techniques and also have a sense of geometry. What I mean by that is you don't need a course in geometry for this section, although it's important that we stay vigilant in our logical implications. Okay, and now we're told to evaluate this integral here, this double integral, where x ranges from x equals y to x equals root pi, y equals 0 to y equals root pi of cosine x squared dx dy. Okay, so now we're told that we're supposed to integrate with respect to x first, although I can't really think of an integration technique to solve this integral cosine x squared. This might not be possible, so I think we're going to need to switch our bounds. Now, it's not, we can't just simply switch our bounds and then switch our differentials. We need to look at this geometrically. So I'll draw my set of axes here. Okay. And now what we're saying is x equals y. I'll go ahead and draw this in yellow here. X equals y will look something like this. Okay. Let me go ahead and label my axes. This is the y-axis and the x-axis. And x equals root pi, I'll put it as a different color here, say red. X equals root pi is this line here. I'll call this x equals root pi. Oopsie, redraw it. Root pi. And the coordinate that we have here, I'll draw a point here. If x is root pi here, I guess if y equals x here, then we have y equal root pi as well. Okay, now for this integral here, it looks like we did horizontal strips since we evaluate dx first. So, looks like we did horizontal strips, but this integral is not it's not computable. So instead, if we do horizontal strips, we might be able to compute this and integrate with respect to y first. Now we'll go upper curve minus lower curve for this. We do cosine x squared dy dx. It looks like the upper curve in the y direction is this y equals x line is the upper curve. And the lower curve is just going to be y equals 0. And x ranges from, well, 0 to root pi. That's the interval there. Okay. And so we'll go ahead and take an integral of cosine x squared with respect to y. And that'll just be cosine x squared multiplied by y. Evaluated from 0 to x. Cosine x squared. Plug in our bounds, and we'll get just an x there. 0 to root pi x cosine x squared dx. This is a u substitution. Let me move my pad here. So we'll let u equal the inside function x squared. Du is 2x dx. So this factor of x will cancel this x, and dx is du over 2x. Okay, continuing, we'll get a factor of half, and when x is 0, u equals 0, and when x is root pi, u equals pi of just cosine u du. And the antiderivative to cosine u is positive sine u. evaluated from 0 to pi, and and it looks like we just get 0 as our solution. And now for this fifth and last example of this video here, we'll take a double integral of e to the x to the fourth power dx dy, where x is ranged from the cube root of y to 2, and y is ranged from 0 to 8. Okay, I don't think I can think of a way to solve this integral with respect to x first. So if we switch the differentials and integrate with respect to y first, this thing, if we're doing the partial integration with respect to y, the variable x, this function, this exponential function, is going to be held constant. So let's go ahead and look at this geometrically. Go ahead and draw our axes here. So the question is, what is the cube root of y? What does that look like? One might ask. Well, if we say x equals the cube root, oopsie daisy. X equals the cube, why can't I do it? The cube root of y. If we cube both sides of the equation here, now we have y equals x to the third, and that is a graph that I definitely know how to graph. So let me just switch over to yellow here and go ahead and graph this, make it go through the origin. This is y equals x cubed, and looks like we also need to graph x equals 2. Okay, I'll do it in green here. X equals 2 is this vertical line, and I'll call it x equals 2. Now, if this coordinate here where the green meets the yellow here, we have a x component of 2, and when x equals 2, y equals 2 cubed, which is 8. And it looks like, for this interval here, y is ranged from 0 to 8. This isn't really to scale, okay? And now it looks like we're integrating this region where we've done, looks like horizontal strips. This horizontal strip, again, this horizontal strip here, it doesn't make my integration nice. So instead, what I think I'm going to do is vertical strips. Okay, I'm going to do vertical strips this time, and if I do that, then I need to integrate e to the x to the fourth dy dx. Now our upper curve is, I guess, is this yellow curve, x cubed, and our lower curve is this y equals 0 line. And it looks like x is ranged from the interval 0 to 2. Oopsie, didn't mean to do that. 0 and 0 to 2. We'll go ahead and partial differentiate with respect to y. Now this exponential function is going to be held constant since we have a variable x here. So we get the integral from 0 to 2 of y ranged from 0 to x cubed e to the x to the fourth dx. Plug in our bounds once more. Okay, so it looks like we have an x cubed e x to the fourth dx. Now I can see the u substitution involved. Let me just scroll down here. You can see the u substitution involved, and we'll let u equal x to the fourth. du therefore is 4x cubed, so we'll have a factor of 1/4 out front. And, it's cube dx. dx is du over 4x cubed. So we'll get 1/4 multiplied by the integral of e to the u du. Our lower limit, when x is 0, u is 0. And when x is 2, we get u is 2, 4, 8, 16. Okay. Antiderivative of e to the u is just e to the u itself multiplied by a factor of 1/4, ranged from 0 to 16, and we'll get 1/4 multiplied by e to the 16th minus 1, and here is our solution. Okay, and thanks for watching. Have a good day, and please subscribe.